Hello, everyone. I'm Namrata. I'm a grad student in computer science at UBC Okanagan. And today I'm going to present my research on this paper as part of COSC 590 this term. So the paper we are going to discuss today is a linear time approximate convex envelope algorithm using the double LFT with application to phase separation. All right, so let's get started. So, what we are trying to achieve in this paper is to approximate the convex envelope of a given function. And in order to do so, we are going to study the double discrete Legendre-Fenchel transform. And we are going to basically compare three different algorithms which are based on discrete LFT. So, just to give a background, these algorithms were originally coded in Fortran by the authors of this paper. And I was fortunate enough to have gotten in touch with one of the authors in this paper who was very helpful and helped me with the original Fortran code. And henceforth, I have read the paper, understood what it's doing, and re-implemented and translated the original code to MATLAB using object-oriented programming. And I have also reproduced the results that were provided in the paper and have confirmed them. All right. So in order to just figure out the terminologies here, what is the convex envelope? So let's say you're given this set of points. For this set of points, this is the convex hull of this set. So you can actually imagine a few nails that are on the wall. And if you try to put a rubber band around those nails, what you get is the convex hull of those nails. So that's the convex hull of a set, and the convex envelope of a function can be shown as follows. So if you're given this piecewise function, the convex envelope of that function is basically this. So it's the greatest convex function which is upper bounded by the function f. Right. So now we'll look into what is Legendre-Fenchel transform. So given a function that's defined as such, this is how we find the Legendre-Fenchel transform, and we represent it as f star. So f star is now a closed convex function, and if you actually apply this LFT to f star, which makes it f double star, that is basically the closure of the convex envelope of the function f. So that is, now we just talked about dimension 2. So for n greater than equal to 2, LFT can actually be factorized along each dimension using this formula, where I is ranges from 1 to n, and that's how you calculate LFT along each dimension. So what we are interested in is the discrete LFT. So in order to define the discrete LFT, we are going to bring in this set omega, which is a subset of Rn, and we can define the function on set omega as this, where the function is f of x when x is an element of omega, otherwise it's infinity elsewhere. So if we apply LFT to this particular function, this is what we get. Now, since we are interested in computing the LFT numerically, the case in which omega is finite is particularly important. So we consider this finite set omega n, which is again a subset of Rn. And now computing the LFT of the function f on the set omega n is called the discrete LFT. So that's what we are going to use going forth. And here the subscript n is actually used to stress on the finiteness of the set omega n. All right. The next is the double discrete LFT. So let's consider the problem of computing the convex envelope of f given omega set. So firstly, we discretize this problem by considering the finite set omega n, as we saw in the previous slide. And we are going to, what we are trying to do is we are we'll be choosing to approximate the convex envelope of the actual function using the function on set omega n. So as we have seen, the application of two successive LFTs to f omega n actually yields this convex envelope, conv f omega n. So here we are trying to build an approximation of the convex envelope by using two successive discrete LFTs. So this is what we do. Now this we have already seen. We are applying another discrete LFT on top of this. And what is SM? SM is again another finite set, which is a subset of Rn. And this SM is called the dual grid. So this is an important one, and we are going to use this in our algorithms. So the omega n is called the primal grid and SM is called the dual grid. And since we are applying the discrete LFT twice, we call this operation the double discrete LFT. And as mentioned, the a correct choice of the dual grid is very essential in order to obtain an accurate approximation of the convex envelope, because at the end of the day, we are trying to approximate the convex envelope, and choosing the correct dual grid actually makes a lot of difference. So we can actually say a set S is the optimal dual set of with respect to omega if it satisfies this. That is applying this double discrete LFT, we should be getting the closure of the convex envelope of the function on the set omega. All right. So these are the three algorithms that we are going to talk about. But before going into that, we have spoken a lot about the convex envelope and what we are trying to achieve at the end. It's obviously better if we can have a visualization of the same. So consider this particular function. As you can see, there is a bump to a upward bump in this particular function, which means it's of course not convex. So in order to find the convex envelope of this function, we apply these algorithms and look at this beautiful convex envelope, and that is going to be our output. So that's what we are trying to approximate. Given any function, we are trying to approximate its convex envelope. You can see this portion is completely flat, whereas this portion has an upward bump. All right. So going into the first algorithm, here we are again applying the double discrete LFT. So let's consider a function f, and let's say the primal grid is this and the dual grid is this, and the algorithm evaluates LFT on f of omega n on the grid Sm, and then it applies the double DLFT on the grid omega n. So a simple choice of the dual grid is basically the uniform discretization of this particular set. And how do we get these values? So these values can be found by computing the interval containing all the natural grids of the one-dimensional discrete LFT along each row and column. And we should note that since in one-dimensional discrete LFT, those grids correspond to the slopes of the convex envelope. So let's say Sm is a grid with the same size as that of omega n. So let's consider the size of Xn is equal to n and Yn is equal to m. We'll then have a total m discrete LFTs on data of size n and n discrete LFTs on data of size m. So we already know that the one-dimensional algorithm's complexity is linear, and hence the complexity of a two-dimensional algorithm based on this factorization would be O of n into m, which is again linear. All right, so that's standard factorization. Now coming to alternating factorization, in order to implement the alternating factorization, we actually take the standard factorization into consideration, and we condense the two consecutive one-dimensional discrete LFTs that we did earlier in the same direction into a single application of the convex envelope operation. So the computation of this alternating factorization is not only slightly better, but also faster when compared to the standard factorization algorithm. So we'll actually look at a pseudocode in the next slide and explain the same. So let me tell you the one-dimensional convex one-dimensional algorithm that is mentioned here as fast DLFT. It actually initially calculates the convex hull and then finds the conjugate. And here is a visualization as to how the convex hull in one dimension gets calculated. So in the alternating factorization, we take in these inputs, that is the X grid, the Y grid, and the functions values calculated on X grid into Y grid. So what we do in the alternating factorization is we first compute the discrete LFT along each column. And here we are calling this fast DLFT function, which first calculates the convex hull in 1D and then finds the conjugate. And this is the visualization of finding the convex hull in 1D. And then once we find that, we build the dual grid, which is very important in our case. And once we build the dual grid, we are evaluating each of the discrete LFTs on it. And then we again compute the convex envelope on each row. This convex envelope is same as this visualization that you see. And then finally, we compute the discrete LFT along each column. And that is basically the second time you're applying discrete LFT. That is what we are doing. We are calculating the double discrete LFT. So that's alternating factorization for you. And next we have the last algorithm for this paper is the max alternating factorization. It's basically a variation of the alternating factorization. So it basically changes the factorization order, and in order to get the result, it merges the result into a maximum operation. So let's say you compute this first, and then you compute this. In order to find the max alternating factorization, we are going to take the max of these two. So that's what we have for this algorithm. And here you can see we are using CM into R and R into DM. But as we all know, R is an infinite set. So in this algorithm, we are actually using finite sets CM and DM and not the infinite sets R. So as we have done our experiments and found out, the results clearly suggest that the alternating factorization algorithm has been improved a lot by the max alternating factorization. It actually, the max alternating factorization gives a higher accuracy than the alternating factorization, since the dual set has been enlarged, and it's also more efficient in terms of computational time. So we choose the CM as the discretization of this and DM as discretization of this, as we already saw earlier. And just to mention that the implementation of this algorithm need not be done separately. We can reuse the alternating factorization algorithm. It suffices to just change the order of the dimensions. Use the transpose of the data matrices before and after the alternating factorization algorithm. So finally, when the max alternating factorization is applied to functions which are invariant under swap of coordinates, the max alternating factorization algorithm preserves this property as the exact convex hull does, which is great. All right. So now the fun part. We are going to apply these algorithms to certain examples that have been also shown in the paper. So we are going to use this particular function first. This is a pretty cool function where we see there is an upward bump in this circle and there is a downward bump here. So as we can clearly see, this upward bump part is non-convex, and in order to find the convex envelope of the same, we find this beautiful convex envelope. And here the bump has been removed and we have this convex envelope here. Now, I have reproduced this as well from the paper using my MATLAB code, where what we are trying to do is we are trying to find the non-convexity region of a given function. As we saw in this circle part is obviously non-convex. So we are trying to see using each different algorithm what is the non-convexity area. So the white portion in the picture actually refers to the non-convexity area. So this one is is produced by the standard factorization algorithm, and as you can see, it's very unclear as to what this is showing. There are a lot of white parts which it's saying is non-convex, but it actually is not. The alternating factorization algorithm does a better job. However, here it's a little messed up. It shows that these portions are non-convex, whereas it's not the case. But as we can see, the max alternating factorization gives a really good result, and we get the actual portion which is not convex. So the max alternating factorization algorithm is doing a really great job. And this has been calculated on this domain of minus 3.75 to plus 3.75. And I've also reproduced the same for these particular domains, and you can pause the video and take a look at it, how it looks. We'll move over to the next example, and here is my next example. We have another non-convex function here, and we have successfully found the convex envelope of the same. And here you can see there's a slight upper bump, and here it's straight, and that's the convex envelope. Then the third example is this one, and this is a pretty nice and weird function. You can actually see there are straight lines coming up in this function. So if we make this graph flat, you'll actually look, there are these circles, these are actually protruding upwards, which makes this function a non-convex function, whereas the convex envelope that is being created is another smooth convex envelope, which is really nice. And going forward, we will also look at the non-convexity region produced by each of the algorithms. And this is what we get. The standard factorization gives us these white regions, which it says are non-convex, which is not the case. And the alternating factorization gives the better approximation of the non-convex region. As we can see, these circles which are non-convex, and the max alternating factorization does a really great job again. And we can clearly see the areas which are non-convex. So finally, what do we see as the result is that here is a simple function f1, here is another complex function f2. The alternating factorization actually does outperform the max alternating factorization for simple tests such as f1, but it's much slower when it's applied to slightly more complex tests such as the f2 function. All right, in order to conclude, I would like to mention that these code were originally written in Fortran, and I have worked on translating and re-implementing the code in MATLAB using object-oriented programming. And I have also reproduced the algorithms on the test functions which were mentioned in the paper, and I have confirmed the results from the paper. And right now, the MATLAB code has now been put on GitHub and is made open source under the GPL v3 license and can be accessed in this link. I would also like to mention that the paper also does an application of these algorithms to phase separation in ionic solutions, but those could not be reproduced due to unavailability of data. All right. So last but not the least, I would like to make this acknowledgement. I would like to thank my supervisor, Dr. Eve Lucet, who has guided me through COSC 590 and has helped me wherever I was stuck. He has helped me throughout. I have worked in the Kokana lab, and I'm thankful for my funding from NSERC, which supports my master's program here at UBCO. And last but not the least, I would like to thank the authors of this paper, especially Lorenzo Contento, who was very helpful in order to provide me with the original Fortran code, and I could proceed from there onwards. So thank you. Thank you everyone for listening to my presentation today and watching this, and have a great day. Thank you so much.